Good. It's 2 o'clock. Good afternoon, everybody. So it's time to get started with our session here. Thanks for coming. So today we are going to talk with two awesome customers, Bosch and BMW, about the next generation of vehicle technologies, with specifically focusing on machine learning, right? Artificial intelligence and so on. So the agenda here, I'm going to introduce them, contextualize, and create a little bit of context of what they are talking about, and talking about this big data loop. We'll see that later. And then BMW will talk about their connected AI platform, and Bosch will introduce how AI is extending from cloud to the embedded edge, and how they do that through BlackBerry IVY and other techniques. And then just a brief summary. But let's get started. So hi, everybody. I'm Stefano Marzani. I'm the worldwide tech lead for SDV in AWS. What's SDV? It's our approach in developing automotive software. And here you see our automotive development infinity workflow, right? This is the diagram that we always use with customers when we present our services for automotive. And you see how it works. You have your devices, the customer devices on the left, can be some developer desktops, evaluation kit on the desks. It can be hardware in the loop rigs, test fleets, production fleet. All this system exchange data with our loop, with our infinite diagram, right? And here inside this diagram, you see our services that are used for a customer first to do some data management, data processing, analytics. And when the data is well prepared, we produce tags, metadata. We store this metadata in databases, raw data on S3 and so on. All becomes part of this super important construct, automotive data lake. And this data is made available to the entire organization. BMW, by the way, has a beautiful case on this in a keynote talk 2 years ago at re:Invent. And when the data is there, it's used by customers to do several things. We have customers like Here Maps or Mobileye that create HD maps. We have customers like BMW or like Toyota that use it to create machine learning algorithms. We have other customers that start to use it to do really automotive hard stuff like powertrain algorithms and exercise this algorithm in the cloud, leveraging cloud scalability in order to achieve better performance and see how that is optimized for the real vehicle. When the software is ready, there are two really automotive specific phases: simulation, and verification and validation. Automotive is a regulated industry, so we need to make it sure that the software that goes inside the car is safe, right? Paramount. And then software is deployed on the left, and everything starts again, right? So data is collected, used to train, create software. Software is deployed, and so on. For this specific talk, the focus is on machine learning. So on the right side of the diagram, to start with, and probably you're familiar with AWS machine learning stack. 3 layers, right? From a machine learning practitioner, the very bottom, they can select the framework that they'd like to use, up to SageMaker, maybe with data scientists. They don't want to go really into the details of the frameworks. Or AI service. You have developers that know nothing about machine learning frameworks, but want to use some high-level APIs, like recognition, to recognize scene images inside an image, right? And do this kind of stuff. And this is really the focus of the BMW talk that you will see. The colleagues will jump on the stage in 5 minutes to talk about it, right? To talk about how part of these services are used in BMW to exercise, to create models, to create artificial intelligence that can be used to achieve insights and other important information for the customers. Then, another step. Very recently, we started to talk and see more and more about this big loop. To be honest, this is a term introduced by a very nice blog post from Porsche Engineering last year, and refers to the fact that we really start to see a need to look deep into the ECUs, in the electronic control units, in the computers that are inside the car, right? So you see that these computers are connected with sensors that collect data from LiDARs, cameras, radar, GPS, and so on. And they actuate the car. If we are talking, as in this example, about an autonomous driving ECU, they really control the steering wheel, control the pedals for acceleration, braking, and so on, right? But what does it mean to look inside? And what does it mean, this big loop? It means that we need to have more sophisticated edge logic inside the ECUs themselves that works in a really, really tight cooperation with the artificial intelligence and machine learning content we are defining on the cloud itself. Let's make this example. Here you see two functionality, for example. One is this edge intelligent agent, so some intelligence that is integrated inside the electronic control units that can do two things. Observe the actuator sensors and decide if the data is interesting to be collected and sent to the cloud, right? You know that doing autonomous driving is pretty expensive. So the best form of saving money is not collecting data that is not useful to achieve more, more sophisticated machine learning models, right? Not collect data, it's not interesting. And this edge intelligent agent can do that. And you will see that applied in a slide. Or another thing that can be done is observe two versions of the software. This is called shadow testing or silent testing. In the ECU, you deploy a more advanced version of, for example, your perception algorithm, and you compare it with the output of the algorithm that is currently in production. There are discrepancies. Are there discrepancies between the two outputs? Collect the data, send it over, so we can have an insight why the two systems have different performances. So you see how the relation between cloud and the embedded edge become very intertwined. It's not just creating machine learning in the cloud or the embedded edge, or it's really exercising the whole stack of technology from cloud to the embedded edge. And here we co-developed with BlackBerry a framework called IVY, that we call it a middleware for the big loop, exactly that, because IVY with the BlackBerry IVY Edge, it's exactly an example of this intelligent agent that can be deployed at the embedded inside the car and provide insights and provide virtual sensor capability in order to discriminate, again, if a data is relevant or not, and send it over, or analyze the performance of a software model that is being deployed in the car. IVY has a cloud component as well, and we will see how Bosch leverages it in this slide to implement their machine learning from cloud to edge in an integrated way. So with no further ado, I'm going to introduce our speakers for today, the real stars of the session. And we'll start with Tin Lian from BMW and Andreas.
Hi. Hi, everybody.
Thank you, Steph. How do we scale AI for our customers so that they have the best experience possible? Hi, my name is Tin Lian. I'm the product owner at BMW.
My name is Andreas, and I'm Cloud Solution Architect at BMW.
That's our plan for today. Let's get started to tell you about the motivation for the BMW Connected Al Platform. Then we'll deep dive into the architecture, tell you about the user interface, what does it look like for our stakeholders, the data scientists, and we wrap it up with a conclusion. So, what was our motivation? Our goal is always to have the best connected experiences for our customers. AI plays a big role in this. So that's why from an early phase, we had the challenge, how do we scale AI throughout BMW? When I'm talking about connected experiences, there are a lot of areas, a lot of connected services. So I'm showing you some of the examples here. With the top picture, imagine yourself being inside the car, driving in a city you are unfamiliar with. We support you finding the right parking space, finding the gas station or the charging station. You can interact with our BMW Intelligent Personal Assistant or the My BMW app. We schedule for you the right service appointment at the right time. So, of course, AI does not come for free. There are some requirements tied to it. I think about data provisioning, data privacy, security, feature engineering, model training, cloud infrastructure, just to name a few. You cannot be an expert in everything. The good thing is, you do not have to be. And this is why we developed the BMW Connected AI Platform, where we bring together the world of a DevOps engineer who really cares about AI infrastructure, who is a cloud expert, who cares about infrastructure as code, who wants to maintain this infrastructure. On the other hand, you have the data scientists. They want to create new machine learning models. They want to program, implement in Python. They want to use all the AI tools they are familiar with. So what we are making sure at the Connected AI Platform is that both can focus on their expertise, do what they want to do, what their mission is, and they do not need to take care of the other side. So this is how we scale AI. We implemented a 3-layer concept. At the very bottom, it's the foundation, it's AWS. So it really starts with an AWS account of a specific use case. This gives our stakeholders, our data scientists, the freedom to use everything they want to do and have all the flexibility within their own AWS account. For the DevOps engineers, on the other hand, it really lowers the risk during operation because the Connected AI Platform is a distributed system. In the second layer, we are talking about the platform layer. So platform as a service. We first deploy in this AWS account the Connected Services Cloud Platform. This is a well-established platform at BMW where all the microservices are currently already running on. Why are we using this? Because the infrastructure is already there, so we just take what's available for us. On top of this, we deploy the Connected AI Platform. That means it's an extension to the existing infrastructure. So we make sure that all your AI tools are available here. And the third layer, the top layer, that's really where our data scientists come into play. So these are all the use case teams. They have a simple user interface to our platform. They can develop their AI applications without worrying whatever is happening underneath. So I hope you are curious enough now to learn more about this purple block. So that's the Connected AI Platform, and I hand over to Andreas.
Okay, yeah, I'm gonna explain you the architecture of the Connected AI Platform. This is the architecture of the Connected AI Platform. On the left side, you can see the data source. We get all our data from the vehicle fleet, and it's millions of vehicles. We have two kinds of data. We have historized data, and we have live data. We use the historized data mainly for model training and for batch inference, and we use the live data mainly for live prediction. On the right side, you can see the consumers. Here we have 3 different kinds of consumers. We have the vehicle fleet again, we have the My BMW app, and we have like the customer portal. And they receive the prediction results from the Connected AI Platform. In the middle, you can see the Connected AI Platform. As already said, it's based on another platform, the Connected Services Cloud Platform. And this was a platform which was developed for microservices, and it's based on Kubernetes. And we just built our Connected AI Platform on top of this platform. This microservice platform offers some capabilities we just want to reuse, so we do not have to reinvent the wheel. The heart of the Connected AI Platform is Kubeflow. Kubeflow is an open source machine learning framework which you can use to deploy and analyze your machine learning workflows. The Connected AI Platform also comes with a notebook server, because before you know how your machine learning workflow looks like, you need to know how your data looks like. So you can use Jupyter Notebooks to analyze and explore your data, and also to evaluate your machine learning steps. The good thing about Kubeflow is that you can not only use it to spawn jobs within the Kubernetes cluster, because Kubeflow is running within the Kubernetes cluster, you can also use it to spawn jobs of any AWS service. And as you can see here on the top, the microphone? Okay. As you can see here on the top, this is just an example. We spawned 3 SageMaker jobs, one for pre-processing, one for feature engineering, and another one for model training. And as a fourth step, you have a glue job, which is used for post-processing. But you can use Kubeflow also like to spawn EMR jobs, for example. So this is not limited. You just need to have the right component. When it comes to model deployment, then you can deploy the model within or in the Kubernetes cluster, and this has one advantage. The model can interact with other services that are already running in the cluster, because in most of the cases, a machine learning application is not just a model, it's more. And another important thing you have to know is model monitoring, because you have to monitor your model. Because models will not be good forever, so you have to check them regularly, and when they are not good enough anymore, you have to rerun your training pipeline, and you will have a new model, which is based on new data. At the bottom of the slide, you can see on the left-hand side, you can see the data scientists. On the right side, you can see the DevOps engineers. And the DevOps engineers are mainly responsible for implementing and also for provisioning the platform into the use case owner's accounts. They do this mainly by a CI/CD pipeline. On the left side, the data scientists, they implement the use case. So they are responsible for implementing the use case and also for setting up the different pipelines on the Connected Al platform. On the next slide, I'm going to show you a short video and show you how the Kubeflow UI looks like and how a pipeline looks like on Kubeflow and how such a pipeline can be created in Python. So this is how the Kubeflow UI looks like. It had different menus, and you can, and I just show you a short video. I will start it. In the first, we just select a namespace on the top, which you can see here. And the namespace is a use case. So you can use the Connected Al platform to implement several use cases on it. And they are all separated like by roles and rights concepts so that they cannot interact with each other. So here we select a use case. You can see the different use cases that are like here in place. And we select the AI use case. And now we are interested in the pipelines. So we go to the pipeline. Here you can see several pipelines. I just picked two. We have a serving pipeline, and we have a training pipeline. So we can just open it. We can see they have different versions. And this is the git commit hash, which you can see here, the version. And here we have the training pipeline. Now we want to focus on the training pipeline. How does it look like? So we just go to the latest version of the training pipeline. And you can see it has different steps. This is the pipeline definition. So you can see it has a data load step, a feature engineering step, a training step, and evaluation steps. And also a staging step. So when the model is good, it will be staged. In this case, it means it will be copied to an S3 bucket. And then we go to the to the serving pipeline. And this is just a two-step pipeline. It just converts the model, and then it will be deployed as an endpoint on the Kubernetes cluster. This was just the definition. And how does a pipeline run look like? This is a pipeline run, and you can see the green dot and the status of it and some other metadata that this was successful. And we can also check like the single steps of this pipeline. Here's some metadata, and you can see how long it took and when it was started. And now we can just check the run, and now we can see that every step of this pipeline was successful. This is how the pipeline looks like on Kubeflow. So you can use it to deploy machine learning workflows and also to analyze it. But this is not done by drag and drop. We need to do it in Python. And therefore, we just connect to a Jupyter Notebook. I can show you how this is done in Python. And then we connect to it. This will maybe take some seconds. And we already cloned a GitHub repository, which is used by the use cases, into this Jupyter Notebook. And now we are interested in the pipeline. So there's a pipeline folder, the ML pipeline folder. We just jump into it. And then we can see like different pipelines. Like there's a batch inference pipeline. There's also a serving pipeline and also a training pipeline. And some common folders here. We are interested in the training pipeline, and so we just go into the Python file. And here the interesting part comes into place. We use SageMaker operators. This means that we just define operators that will start SageMaker jobs from this pipeline. So we have a processing operator and we have a training operator. And we will use them in the different pipeline steps, or in some of them. And here you can see how to define them, and then we go to the pipeline definition. Here it starts with the data load step. And then you can see this uses a processing operator. So it will spawn a SageMaker job for processing the data load step. And then after this step, there's a feature engineering step. This will also use the processing operator, and it comes right after the data load step. This is defined here. And now there's a training step, and guess what? It uses a training operator for model training. And this is followed by the evaluation step, evaluation check step. This means you can check your model, and if you met the thresholds, or if the model is good enough, then it will be staged and copied to an S3 bucket. And this definition of the pipeline in Python just needs to be pushed to the GitHub repository, and then GitHub Actions will come into place, and the pipeline will be created on Kubeflow, and then you can use it and restart it. This was just a short video, and now Tinjan will show you or explain your use case, which was already implemented on our platform.
So far, we've shown you the Connected AI platform in general. Now we want to go to a specific example from our pre-development to show you where's the benefit if I use the entire AI workflow. Where's the benefit for our customer? Where's the benefit for you? So the example we are presenting here is the smart vehicle maintenance. It all starts on the top with the customer. So it's crucial here that we get the consent from a customer, from you, to collect your drive data in the vehicle. The drive data in the vehicle is then transmitted to the cloud. In the cloud, we have the DevOps engineers improving, maintaining our Connected AI platform, and we have the data scientists. Now specifically the data scientists of the team Smart Vehicle Maintenance. And they developed two Kubeflow pipelines. The first Kubeflow pipeline takes all the vehicle data to train a machine learning model, and the second Kubeflow pipeline takes your specific vehicle data to predict a maintenance need. If we identify that your vehicle needs some maintenance, this information goes then to the service consultant. The service consultant will proactively reach out to you via the best communication channel and schedules a service appointment for you. In that way, your car has been taken care of even before you have noticed anything. Just make sure you don't ignore the call from the service consultant. We saw in the use case, when we talk about AI and data, this comes with a high responsibility. That's why it's important for us to let you know we highly value customer choice and consent. We apply privacy by design, and we developed at BMW a code of ethics for AI. If you're curious to learn more about it and read more about it, please feel free to take a picture of the QR code and read about the 7 principles. So here we go. We have shown that the BMW Connected AI platform can scale AI for our connected vehicle to get the best customer experiences. Within the Connected AI platform, we have DevOps engineers and data scientists. They both focus on their expertise. AI and non-AI use cases run under the same infrastructure. So the non-AI use cases are all the microservices. In that sense, we make sure that they can smoothly interact with each other. Not every use case has to have AI in there. We also showed that AWS and open source integrate well. We showed you the example of the Kubeflow pipeline that spawns a SageMaker or a glue job. Because they integrate so well, we really can have the best of both worlds. AI comes with responsibility, and we take it. So what's up next? We will globally roll out the Connected AI platform in all our connected drive markets, and we keep on pushing, improving our customer experiences by applying AI. Thank you very much.
Thank you very much. Hand over.
All right, hello and welcome everybody. First of all, thanks to Stefano for organizing the session and also to the BMW guys and girls. I think you made my presentation way easier because you explained a lot of the tech behind it already. So what I want to talk about is today how we at Bosch collaborate, in this case with AWS and BlackBerry IVY, to enable the data utilization and therefore unleashing the innovation power not only of the OEM or the supplier base, but also the overall developer community. My name is Stefan Börkel. I'm working at Bosch. I'm responsible for the sales in North America for all our electronics and software products. So before I start digging in, for those ones who are not so familiar with Bosch, let me give you a quick few data points. We are worldwide 400,000 employees. You might know us in the automotive industry, which is our biggest sector, but also in the power tools, households, industrial goods. We are quite at home. We have 76,000 engineers working for Bosch worldwide, and thereof 38,000 software engineers. And we will see how important that is, because if you think about today, already 90% of all innovation in the automotive market happens in the software and electronics space. And that's a good trend because we are way quicker in software to bring innovations into the market than on hardware or mechanic-based solutions. We are represented in 60 countries in over 130 locations, which really allows us to collaborate with our customers and our partners where they reside, as these collaborations are becoming more and more important, as you will see later when we talk about the software-defined vehicle. The ties and the split, the workload split is shifting completely. So before we go into the detail, let me put the frame a little bit about what's happening in the automotive industry. As I mentioned already, 90% of the innovation is happening in the software and electronics space. So 2010, an average car had approximately 10 million lines of code. Today, we are approximately around 100, and the projection is that going towards level 3, level 4 autonomous driving, that will go up to 300 to 500 million lines of code. Now, alongside with such a sheer huge amount of software, of course, comes the compute power. And so far, the approach in the industry was that we were developing functions dedicated to the area where we want to have them, like safety features, forward collision warning, lane assist, or in completely different domains in the interior side, infotainment, driver monitoring. And each of those domains had their own ECU. So what obviously happened as we increased the features in these fields over the years, the amount of ECUs went up to compute all the software we created. So meanwhile, a well-equipped car has up to 100 ECUs, which drives a lot of complexity in the vehicle, which becomes hard to manage not only in the very classical engineering domains, like managing the power consumption, managing the thermal aspect of it, or just designing the wire harness for 100 ECUs. It also makes it very complicated to enable those 100 boxes to communicate with each other. Of course, we have CAN, we bring Ethernet to allow that, but you can imagine if it's that distributed over the car, you never utilize the full power of the data you actually have. Also, to give you the last data point about a vehicle, we have approximately 80 sensors delivering 130 sensor data points, different sensor data points in a vehicle. So when we talk later about a new architecture, which is often referred as a software-defined vehicle architecture or the smartphone on wheels, I personally think that we are way beyond the smartphone on wheels. We're also a smartphone and a smartwatch and glasses. If you think about how many sensors you have in a car, which not only give you input about what's happening inside the car or what happens with the people in the car, but also the whole surrounding of a car. And what the possibilities with all this data you have, and we saw use cases presented by BMW, you really want to go in a direction where the smartphone also went, but we will talk about that. So let me get back to the E-architecture and animation. So what you basically see is the shift from a decentralized architecture to a centralized architecture, which we refer as a domain architecture. So moving the 100 ECUs to a few very powerful vehicle computers, typically 2 or 3 of them, just depending a little bit on the design by the customer, supported by zone modules, which are then located in the area where the sensors and the actuators reside. They collect the information, share it with the domain computers. So that brings 2 major benefits. The one is it makes it way easier to implement third-party software modules, as now all the software stack is one holistic architecture in one domain computer. But also now all the data is flowing centrally together to these domain computers and are way easier to harvest in a sense of creating good services for your end customer. So with this change, of course, and you will see I lead up with all the sensors and all the data, it becomes important when we talk about collaboration together with BlackBerry IVY and AWS, how we want to implement, together with machine learning, a solution in the car to tap into the innovation power of the overall industry. So another data point is, so Bosch is producing 4 million sensors on a given day, covering 70% of the portfolio of a car sensor demand. And with this of course allows us not to understand only the domain computer side and the software architecture on it, but also all those different types of sensors, if that's ultrasonics, radars, videos, and so on, interior radar, outside radar. So to help creating these features, functionalities, the safety measures, the comfort measures, the entertainment side of things, to bring that together with our partners and customers into the market. So let me get to the core topic and the collaboration, as I mentioned, together with BlackBerry IVY and AWS. I want to span the challenges and the goals. What do we actually want to achieve? The first we want to achieve is to tap into the innovation power of the software community, not only within the customer or the suppliers or the chosen partners, but the overall industry. What we need to do to achieve that is to create an abstraction layer so that the sensors becoming not specific and being usable for everybody, which we refer then as artificial sensors. And we have to create a developer interface so that it becomes simple to go in and use sample data to kind of play around and figure out solutions to ultimately go where the smartphone went. When the smartphone industry created the app stores and the developer interfaces, this is where you saw an explosion of innovation coming along with your smartphone. Today, in the automotive industry, we are still very capsulated. And there are reasons for it, good reasons mentioned by BMW, right? You don't want to just take the data, their privacy, you want to protect it, you want to have it safe. But at the same time, if you want to unleash the innovation power, you have to find a way to share it. And this is where IVY comes into play. So, as I said, let's go into IVY. What is IVY? It's a pre-integrated middleware stack which resides between the domain computer and the use cases you want to create. And we will talk about the software architecture a little bit more in detail, but they almost not needed anymore, as Stefan already explained, how it's in theory set up, but you will see it then in reality. But at this point, I can share so much and talk about it, and I know you can talk a lot, but seeing is always better. So please take the chance. Here, right next to the forum, in the tent next to the Ferris wheel, is a proof of concept, a demo, where you can see use cases already implemented, and you can better understand how it works and get also deeper into the technology. I want to highlight 2 use cases here. Those are the ones you will see in the demo I just mentioned. The one is the analytics and diagnostics, which is supported by us and CompDirect, a company which looks into utilizing the data in the car, and similar to the use case BMW described, is working on using algorithms to do predictive maintenance, to identify your tire wear based on your driver profile. As we all know, driving cars, it depends on how you use your car, has a lot of impact on how your tires are worn down. So you really want to do that based on a user profile. So that is one use case we're showing. The other one is in-vehicle payment supported by Car IQ, which has basically two pieces. The one is the comfort side of things, so that the very well-known use case is to drive up to a gas station. You don't need a credit card or any way you walk in Germany to pay. You just drive up, the car recognizes where you are and releases the pump, you fill up, and it's paid in the background. But the second part of it is that via your driver profile, you can also detect who is driving the car, so the payment is done by the person who's driving the car and not by the car, whoever is in the car, which is also an interesting way to identify who's sitting behind the steering wheel. So those are two use cases we are showing in the proof of concept. A third one, which is not implemented here today, but we are supporting, is the smart parking. Here we utilize our initiative we created with the American Center of Mobility, the state of Michigan, Ford, and Bedrock, where we created a smart parking lab, which basically builds a mock-up surrounding of a real-world situation so that any company, any partner of ours, any other company who wants to test features, functionalities, using the infrastructure which you can find in future around the topic of parking, and basically train, work, test their systems. So everybody's welcome to join and utilize the smart parking lab. So again, this is the proof of concept. You can find it outside, right next to the Ferris wheel, and Stefano will also give you more information where it is exactly. But as mentioned, let me share a little bit about how it is applied in the car and also shown in the POC. On the right side of the picture, on the bottom area, in the gray part, you see the domain computer, which I mentioned earlier in the E-architecture, including the operating system, which is a QNX or a Linux-based operating system. So this is what we, as Bosch, would supply from a product if the customers allow us to. And this is where the input data comes in, either via CAN or Ethernet or directly connected to the domain computer or via the zone, as explained earlier. On top of this, you see the blue parts, which is basically the IVY solution. It consists of two main areas. One is the edge side, and one is the cloud-based side. So let me start on the left side, on the edge side. The edge side, so embedded in your car, consists out of two pieces. One is the vehicle service layer. This is where basically you have all your safety mechanisms, your safety protocols to ensure that exactly as described earlier, all the data is handled in a safe, secure measure and alongside with the consent of your end customers, which is and we fully agree with that, absolute key part to maintain. The second layer is the synthetic sensor service. So let me briefly tap out here and explain one more time what we mean when we say synthetic sensor or artificial sensor. Both words are used. As mentioned, we have these 80 sensors, a wheel speed sensor, a gyro, a radar, a video camera, inward, outward facing, and all different sensors. So all of them, of course, deliver a raw signal, and it becomes it is when you are in that specific field, let's say you are in the field of creating safety mechanisms for collision warning, and you work on a day-to-day basis with an ultrasonic or front radar or video, you know how to use the raw signal, abstract, do your machine learning to derive usable data out of that raw signal to then make the right decision mechanisms to stop a car or slow down a car and so on. Same thing if you do driver monitoring or if you do V2X communication, which ultimately is like a sensor, right? Ultimately, also V2X delivers information into the car, in this case from another car. But let's assume you are a developer outside of the customer or a supplier and you want to create services for the automotive industry. And let's say you want to utilize the forward-facing camera to detect if a car in front is coming closer because you're speeding, that one is standing. And you want to use the driver monitor camera to check if the driver is paying attention on the road or maybe is distracted doing something different. And you want to use the data of the V2X to know that if that car coming around the corner is slowing down or going above the crossing. It is almost impossible for an outside person to do that. You have to be either collaborating heavily with all the different departments of the OEM or the supplier of that system, or you have to be part of one of those two companies. And this is where artificial sensors come into play and the idea of IVY. Instead of using these raw signals to derive the right measures, the artificial sensor is sitting on top in the in the synthetic sensor service layer and creates outputs to be easily used for somebody else. And there could be a synthetic sensor called driver monitoring. An output is distracted, yes, no, or looking left or right, looking down or up. Very simplified outputs to be used as they are, even though you never really look into the signal of the true sensor. So this is what we mean with synthetic or artificial sensors. And this is, of course, where you need somebody who is familiar with the type of sensors you use. Now, the driver monitoring is somewhat simple, right? In a sense, you can imagine not so difficult, but let's talk about maybe you want to use the signal of a NOx sensor. How many people are familiar with NOx sensors and the output of a NOx sensor and how to derive the right outputs and data points of a NOx sensor? So that's why you need companies like Bosch and others who are familiar with these sensors and create artificial sensors to then be used for anybody, which is then released depending on the OEM strategy. So this is what's happening in the synthetic sensor service layer, as well the processing of the algorithms you created to derive connected services, for example. Why it is important that this is happening on the edge? That allows, of course, way less data upload into the cloud, and that's still an expensive thing. So with doing that on the edge, you can approximately save up to 70% of data which you need to upload, while the additional SoC power is approximately 2%. So there's a clear advantage to do that on the edge. At the same time, you don't want to do everything on the edge. And this is where the right side of the picture comes into play. So the two key pieces, the IVY console and the IVY developer tools. And you see already there's a certain similarity from an approach how you also find it in the smartphone market. The IVY console, this is basically the monitor center for the OEM to be able to see what's happening in the market, what data is uploaded, where is the data going, what are the release rights to certain companies, partners who work on the services. And also here, you can activate or also deactivate data availability through the car, which is an important thing. When you produce a car and you send it out in the field, it shouldn't be a one-time thing to say yes or no to a certain data set being available or not. So via using adaptive AutoSAR, supported, for example, by Bosch, you can then actively through the monitors change in the field the data rules and settings how you want them. On the right side, the developer tools, this is where basically your framework is, where you can, via the cloud, download sample data sets to play around in a sense of finding out if you have an idea to create a service or an algorithms. You don't have to do that on the edge, obviously, in a car. You can do that on sample data in the developer tool on the standardized APIs. And then when you figure out how to do it and how the function is deployed and the OEM is convinced that this is a good feature for their app store, for example, then via the console you can update the field in the cars in the field and make the service available, or vice versa if it turns out that something isn't working. And this is basically where the developer toolkit comes into play. So all of that is already available. Unfortunately, we were not able to bring our car over as we just presented it a little bit more than 2 weeks ago at the Bosch Connected World. Maybe you have a chance if you're at CES, please feel free to visit us or the QNX BlackBerry booth, where you see a really integrated solution into the car. The experience, of course, is another step more convincing than a POC, because you really see how it will be in the car. In this one, we implemented also the predictive maintenance, the payment system, but also some parking possibilities. So, to wrap it up, you see a few lessons learned points. I would say they're things which you would expect in such a situation when you create something new. But ultimately, I think all of those challenges you can see on the screen are overcomable. Ultimately, the key question is the industry ready to make data available to the outside community to tap into the innovation power of the people, not only within, but also outside the ecosystem? That will be the key challenge, to do that in a safe and secure way, as I mentioned, in line with what we saw from a rules perspective. But this is where exactly the artificial sensor comes in, because not only it creates easy reusability, because it's not the raw signal, it also detaches the real data information, which might be also personalized, and create artificial data, which is then intended for use cases to be used. So that will be the ultimate challenge. And with this, I would hand over back to Stefano to wrap it up. Thank you.
Thank you. So after all this information from our awesome customers, who has a single doubt that the future of automotive will be infused by artificial intelligence and machine learning in all stages of the life cycle? It's not just in the vehicle, it's outside, in preparation for selling the car, in preparation of informing the user about the car characteristics, managing the interaction with the users and consumers before, during the process of purchasing a car, and then inside the cabin, right, when the person is driving the car, right, and so on. By the way, we presented very recently an artificial intelligence providing a test drive, right, inside the car as well through Alexa. So many usages of it. And after the car is sold, again, how you manage all the processes, after sales, service, all this aspect. And you see all the system, how much they are really tightly closed, interconnected in a big loop perspective, as we explained. So to wrap it up, really, automotive development is now a big loop. AI, artificial intelligence, needs to be designed natively in software workflows, right? This is, I think, the big learning from today. Really, from cloud to vehicle edge and back in all the part of the vehicle or life cycle. And then we, as AWS, support this big loop with the 3 layers that I explained. So machine learning framework, SageMaker, AI services, CI/CD, of course, and with the strategic collaboration that we have with BlackBerry IVY to close the loop inside the car, in the embedded edge, right, to implement this intelligent agent that we express. And in this session specifically, we presented 2 very nice customer cases that covered the big loop, right? So BMW with the Connected API platform that scales really connected vehicle artificial intelligence to improve customer experiences, first and foremost. And then Bosch that uses BlackBerry IVY to offer a platform to deliver big virtual vehicle sensors and more, as we explained. So as Stefan was suggesting, the next step is to meet us. We have really awesome demos at the industry demo tent at the end here is the Caesar Forum. So please come over. I'll be most of the time there tomorrow and the day after. So I'm really hope that I can meet, and if you're interested, we can talk more. There's another important content that we presented just yesterday. We introduced for the first time an AWS workshop that enables you to have a hands-on experience on IVY, right? It's called AUT202. You can look it up. It was yesterday, but very soon we will make it available publicly on AWS workshop. So look out for that. It's a super interesting content where, by the way, we are using QNX as a target OS running natively in cloud. It has been another big announcement from BlackBerry just this last Monday. So QNX, that is a real-time operating system running natively in AWS cloud as a target to design and develop virtual sensors, right? So and that's another big thing that we discovered and presented this week. So that wraps it up. So thank you so much to our customer, to Andreas, to Tin Lan, and to Stefan. It's been great, and we are available here to address any question, just not in the session, but we'll be available outside. So if you want to interact with us, and with the speakers especially, feel free to do so. Thank you very much.